All right, welcome back to chemistry class, except this time I'm on parental leave and I'm talking to you through the screen. So please have some notebook paper out. We're going to jump into Unit 2, all about chemical bonds. This video is going to cover 2.1, 2.3, 2.4. So when we talk about bonds, we're talking about the sharing of electrons. Remember, sharing is caring. And these electrons, when shared between atoms, hold them together. There are lots of different types of bonds. We're going to talk about the three main categories today. And when bonds break and when they form, that's what constitutes a chemical change. If something is changed where bonds didn't break, bonds didn't form, then we're talking about a physical change. So knowing how bonds change and how the electrons sort of move around during these breaking and forming sessions, that's what is going to form the foundational understanding of what a chemical change is, right, on that subatomic level. So our three main types are metallic, ionic, and covalent. We're going to spend a little time talking about all of these. I will say covalent tends to be a little more substantive as far as the year as a whole. We tend to rely a lot on covalent bonding. And yeah, you should understand it because the whole world contains bonds, blah, blah, blah. All right, so what do we need to know in order to access this? I just wanted to remind us, when we say metal, non-metal, what do we mean? Metals are all these in green, right? So everything to the left of that stair-step line that starts under boron and sort of keeps going down. And non-metals are everything to the right. So memorizing the non-metals, pretty easy because there's only, I don't know, like 15 of them. Memorizing the metals is pretty unnecessary. It's just most of the periodic table. But don't forget, hydrogen is a nonmetal, even though it's on the left side. The lanthanides and actinides, otherwise known as your F block, you don't have to memorize those. We don't tend to do a lot with them in this class because they are synthetic or naturally made, so they don't occur a lot in our problems. So we need to be able to identify what's a metal, what's a nonmetal. Let's start with metals and metallic bonding. So in metallic bonding, well, we've got this happening in metals, first of all, crazy. This is going to happen when you have a pure substance. So for example, just a sample of pure copper or pure iron, or we sometimes have alloys, and we'll talk about that more in this video, which is where you have two metals actually mixed together in a certain way. Now, what happens when we have metallic bonding is metals like to form cations, right? If you're talking about copper, copper likes to form a 2+ cation, which means it loses 2 of its valence electrons, right? Now, on the atomic scale, what are those electrons doing, right? It's bonded with itself if it's just copper. So where are the electrons lost to? Look at this diagram and see how the electrons are outside this positively charged nucleus, but they're just sort of migrating around. They're in this, what we call sea of delocalized electrons, right? And all of the cations within this sample of copper, they're all attracted to this sea of delocalized electrons, and that is, again, the sort of glue that holds these things together in a bond. Now, on the macro scale, what do we see as a result of metallic bonding? These are just a couple qualitative properties we need to know about. Lustrous, they tend to be very shiny. Malleable and ductile, not all metals are malleable and ductile, but because they have this migrating sea of electrons, we can sort of morph metals into very specific shapes that they will retain. So something like aluminum is very malleable. That's why we have thin sheets of aluminum foil. Substances like copper are very ductile. We can draw copper into wires. We also see very high melting and boiling points. So this is why in order to melt, iron to make a sword, you need a forge that gets really, really hot because iron has a very high melting point. In addition, metals are really good conductors of heat. This is why we use metal pans in cooking, because they conduct that heat straight from the pan into whatever food you're cooking. But they also conduct electricity very well. And if we look back at this picture, that makes sense, right? Electricity is about the flow of electrons. And these electrons are delocalized and they can move around. So if we apply a current over here, we're going to move all these electrons to the other side or up here, right? We've got a lot of free-floating electrons that can carry a current in a metallically bonded substance. Okay, so these are some of the general properties you should know, and they can help you identify if a substance is a metal, right? Can you just apply a current to it? Will it conduct a current? Then maybe it's a metal, right? So we want to talk a little bit about alloys as well as comparing the strength of metallic bonding. So we can compare, if I give you two metals, based on how big the cation is and based on how many valence electrons that has. So in this image right here, we've got a group 1 metal. We could say this is, I don't know, sodium. And we've got a group 2 metal. So we could say that's magnesium. Why are you not doing what I want you to? Stupid laser pointer. Okay. So let's say this is sodium, and it's taking a +1 charge. And let's say this is magnesium, so it's taking a 2+ charge. Right, so we've got the size of the cation. A smaller cation is going to mean a stronger attraction. Think about Coulomb's law, right? Smaller radius, you're going to be closer to that other charge, so you get a stronger pull. If you're further apart because you have a bigger radius, you're not as strongly bonded together. But also, when we have just a greater number of valence electrons present, you're going to have a stronger attraction because there's more electrons moving around to exhibit some sort of positive, negative interaction, right? A Coulombic attraction with those positively charged nucleus sort of cores, right? So metal B is going to have a stronger metallic bond than metal A because of that. Again, magnesium, when it becomes an ion, donates 2 valence electrons, whereas sodium, when it becomes an ion, only donates 1. Right. So we need to talk a little bit about alloys. Alloys, again, are just when we mix a metal with another element. It's usually another metal, but sometimes we also mix nonmetals into alloys. We've got 2 types, interstitial and substitutional. So those names can give you a pretty good clue. When it's an interstitial alloy, we've got a really big difference in the atomic radius of the atom that's inserted to the primary metal. And because it's so much smaller than the primary metal, it will fit into the cracks. And this will make more sense when I show you the pictures. Usually, interstitial atoms is going to be hydrogen, carbon, nitrogen, or boron. Carbon is often mixed into iron to make steel, right? When we have a substitutional alloy, this is where the atom you're inserting is basically the same radius as the primary metal. And so it can basically substitute and replace certain atoms within that primary metal. So what do you think? Pause the video for a second. What do you think between these two would be a stronger alloy? So if we look at these two images, think about stronger alloy means if I hit it with a hammer, right? If I just smacked it right over here, which one wouldn't be as likely to budge? Well, this one, the interstitial alloy, has fewer cracks between it, right? Because these little cracks are being filled by carbon atoms. And we can see how much smaller those carbon atoms are in terms of radius compared to an iron atom. Whereas down here, we've substituted a copper atom for, I don't know, maybe every 10th nickel atom. And the coppers are pretty close, but they're a little bit smaller. And we see greater gaps because that substitutional copper atom isn't totally filling in all these gaps. So we would say, generally speaking, interstitial alloys tend to be stronger. But you should be able to answer questions where, if I say, hey, copper has a radius of 100 picometers, and nickel has an atomic radius of 102 picometers. Those are pretty close together. If I made an alloy between them, would it be interstitial or substitutional? And you'd say, well, it's substitutional because they're pretty close together in radius. All right, we're going to switch to ionic compounds. So again, start with a micro, and then we'll talk about some macro properties. Anytime you have a metal and a nonmetal, you're going to end up with an ionic compound. And a slight addition here could also be or a polyatomic ion, PAI, right? So it could be a metal bonding with, say, nitrate, something like that. Now, when are ionic bonds formed? When a cation donates its electrons wholesale to an anion that then accepts them, right? So it's a full transfer of electrons from the positive ion to the negative ion. So it's not sharing. We can compare the strength of different ionic bonds using Coulomb's law. Same thing when we were looking at periodic trends. If you have bigger charges among one pair of ions, it's going to be a bigger force of attraction. And if you have smaller radii, so those ions have to be closer together, right? They get a really strong force of attraction. So again, that's Coulomb's law. We never have to plug in numbers quantitatively to calculate it. We're just comparing things qualitatively using where charge and where radius sit in that equation. So on the macro scale, when we think about properties, ionic compounds form crystals. This is why we can see rock candy. Well, actually, no, that's a different kind of crystal. When you see like salt, right, NaCl, you've often got salt crystals. Calcium chloride forms crystals. Lots of different salts do this. Ionic compounds tend to have very high melting and boiling points because the strength of those ionic bonds is really powerful. They tend to be hard and brittle, right? So when you pick up salt grains, they're not going to feel like soft and waxy. They're going to feel kind of hard. And if you had a big chunk of table salt, right, like the big sea salt, and you hit it with a hammer, it would be brittle. It would just sort of like shatter into many smaller pieces. Now, one unique thing about ionics is they will conduct electricity when they are dissolved into water and when they are molten. So again, when I was talking about properties of metals, thinking about if I gave you a mystery substance and said, tell me if this is ionic or covalent or metallic, right? One thing you could do is try dissolving it in water and then plug a voltmeter up to it. Does that solution conduct a current? Because if it does, you might be dealing with an ionic compound. But again, we can also melt ionic compounds. So liquid table salt, not the same thing as table salt dissolved in water, that can also conduct a current. When they are a solid, they can be good insulators, less so when they are liquids or gases. So to talk a little bit more about the structure of ionics, we've got this lattice repeating structure. So it's like a grid where we've got anion, cation, anion, cation, and we can see that here. Yeah, there we go. So chloride, sodium, chloride, sodium. Oh, it's jeepers. Didn't mean to do that, guys. It's 2:30 p.m. What is today? September 12th. Can you believe I'm doing this like 2 months in advance? This is crazy. I must really care about you guys. In ionic solids, there's no discrete ionic molecule. That means there's just this repeating pattern, right? It just keeps going to the left, and then it keeps going down, keeps going in, keeps going left. It's just the same pattern repeating. Harkening back to our discussion on particle diagrams in Unit 4, we want to indicate relative radius, right? So I know chlorine's bigger than sodium. I should show that in my lattice structure example. Yeah. All right, so little quiz. Try to take, 2 minutes and answer these on your own. Pause the video. Okay, I'm assuming you paused the video. So calcium oxide or strontium oxide, which has a stronger bond? Well, they both have oxygen, right? So the only difference is calcium and strontium. And if I look at my periodic table, well, calcium has, 4 energy levels as a neutral, so it's got 3 energy levels as a cation, right? 3 ELs. And I want to say strontium will have 4 energy levels as a cation. Again, because each of them donates 2 electrons, their valence shell, they go down to having just the previous energy level. So strontium is bigger. It means it's further away from the oxygen. So when strontium and oxygen are linking up, they're like this. They're a little further apart. Calcium and oxygen are like this. They're closer together. So calcium and oxygen is going to have a stronger bond because radius is smaller. And this pen is real kind of garbaggio. Sorry. Magnesium bromide and sodium bromide. So again, we've got atoms, cations that are different, and they differ in size for sure, right? Every element has a slightly different radius. But what's more important here is that magnesium has a 2+ charge. right? I didn't mention this above, but calcium and strontium both have 2+ charges. So for that example, it wasn't about the Q, right? For that example, it was more about the radius. But for this example, it's more about the Q. The fact that magnesium bromide is going to be stronger is mainly because Q1, right, the charge of that cation, is 2+ instead of 1+. When in doubt, if the radius and charge don't agree with each other, the charge being different should trump the radius. All right, and then a little structure for calcium oxide. So calcium should be bigger, oxygen should be smaller. So I'll just draw like a couple repeating molecules or repeating ions. So again, the bigger atom is calcium, the smaller atom is oxygen. That's kind of it. We're going to talk a little bit about lattice energy. So this is just another way to represent the strength of ionic bonds, and it refers to the energy to separate ions. So we can think of it as two different directions of energy change. One of them is when we combine gaseous ions into an ionic solid, which isn't a very normal thing we can do, but we can do it in a lab setting and measure it. The combining of the ions from gas to solid is like, oh my gosh, what a hard thing I just did. I was gaseous and all these charged particles, and I finally found my home base as an ionic solid. That's a huge release of energy for these particles that are like finally at a stable resting point. Whereas when I separate those ions, that's going to require me adding or having these things absorb energy to make them into a less stable arrangement, right, as free-floating gaseous ions. So lattice energy can represent both of these. I can talk about, oh, the lattice energy is what's released when I bring these gaseous ions back to ionic solid, or the lattice energy is what I have to add to the solid to tear them apart into gaseous ions. We use a slightly modified version of coulombs to indicate lattice energy. So it's a unique K value. We use capital Qs, and we don't square R. But again, this is going to be the same kind of qualitative comparison tool when we say, okay, what's the lattice energy of this compound versus this one? We're not plugging things in. We're just saying, well, if this has a bigger radius, it's going to have a lower lattice energy, stuff like that. So if I go back to these questions, I could literally rephrase that as which has the greater lattice energy, and I would get the same answers, right? Lattice energy and ionic bond strength, basically the same thing. Oh gosh, that's really not okay. I'm sorry, guys. Why are they brittle? Well, if you think about this example where I've got the hammer sort of shifting these ions over, what happens here? Oop, I made some like charges next to each other, right? And they're going to repel, and then you get this whole crack along this line because all these things are repelling, right? Yeah. All right, covalent. Let's do it. I'm gonna get a sip of water. You pause your video or something. So covalent bonds have to happen between two nonmetals. Nonmetals are from that top right corner of the periodic table. And this is all about sharing, right? Sharing is caring. And when we have covalent bonds, we are sharing valence electrons. So they're not hogged by the anion as they are in an ionic bond, although there is some relative hogging when we think about polarity and electronegativity. And that's my next point. So when we talk about covalent bonds, we got two types, polar covalent and non-polar covalent. So let's go into those. Relative electronegativity is what we are looking at. So we aren't often using actual values in this course for electronegativity, but they do have actual values that you can find. So if two atoms have basically the same electronegativity, which again refers to the attraction to electrons in a covalent bond, if two atoms have basically equal electronegativity, they're going to attract the bonding electrons with equal strength, right? So this is how we get a nonpolar bond. This is where atom A is just as greedy for electrons as atom B. So the electrons are going to be sort of stuck in between them. It's like a tug of war where both sides are equally strong. But if they have really different En values, so let's say atom A has like a really beefy bicep and it wants the electrons, and atom B is like, I've never worked out a day in my life, right? And they're both trying for the electrons. Well, the buff atom is going to pull the electrons a lot closer to it. And this is a polar bond because atom B is like still touching the electrons, right? It's still sharing them technically, but they're way closer to atom A, right? So that's a polar bond. And here's a representation. So two chlorine atoms, they are the same strength, right? They're the same, they got the same electronegativity. These electrons are smack dab in the middle. When we have hydrogen and chlorine, chlorine is much more electronegative than hydrogen. So these electrons are going to be much closer to the chlorine atom. Now, I want to note this little squiggle dude. So these are partial charges. Squiggle negative is going to go by our more electronegative element. Squiggle positive, less electronegative element. And we don't see any partial charges on the chlorine-chlorine bond because, again, it's entirely nonpolar. So neither atom has a partial charge. And this is the same too, but I've added in an ionic bond, right? So we can see how the arrangement of electrons does not actually overlap here in the ionic bond, whereas we do have some overlap, but mostly the electrons stay around chlorine in this polar covalent bond. And in the chlorine diatomic bond, equal distribution of the electrons. Yeah, okay, there's some memes. Some more. Yeah, okay. What do covalent compounds look like on the macro level? So they're not lustrous. That means they're not shiny generally. They're sort of like dull colors, but they can be in all sorts of colors, just like dull sort of sheen to them. They tend to be pretty brittle, although they can be hard or soft. Really, the big thing about covalent compounds is they have low melting and boiling points. So think about all the substances that are in like our atmosphere, right? So oxygen, CO2, what else? Methane gas, right? All these things are gases at room temperature, so they must have a really low boiling point, right? Compared to stuff like iron or table salt, these things that are solids at room temperature. Covalent compounds are also known for being really bad conductors of heat and electricity, so you wouldn't want to, say, insulate your house with air, right? You would want to insulate it with something solid, right? All right, what do you need to know from this? You need to be able to distinguish between these three types of bonding. So on the micro as well as the macro scale, thinking about distinguishing their properties. And we want to do some comparisons, right? So using Coulomb's law, if I give you a pair of ionic compounds, can you compare bond strength? Can you compare lattice energy? Drawing some sample structures, determining if covalent bonds are polar or non-polar.